The decision tree algorithm is used to solve classification problems. In KNIME Analytics Platform, the algorithm runs in the background of the decision tree learner node. Today we want to see how it works. The goal is to train a decision tree like the one here on the right. The tree partitions the training set into subsets until each partition is either pure in terms of the target variable or sufficiently small. Pure means a subset which contains only samples of one class. Each partitioning operation can be described by a rule that separates the incoming data based on the values of one feature, the splitting feature. To summarize, we can say that a decision tree consists of three different building blocks: tree nodes, tree branches, and tree leaves. Tree nodes identify the splitting feature, tree branches identify the different values of the splitting feature, and tree leaves at the end associate the final class to a specific decision path. But actually, the tree we see here is not the only possible classification tree. Instead of using the storage feature to make the first split, we could also have used the outlook feature. So how does the algorithm decide when to use which feature in order to split the dataset? The aim of the algorithm is to make the splits in such a way that the subsets are as pure as possible in terms of the target variable. Therefore, at each step, the algorithm uses the feature that leads to the purest subsets. Different metrics and indices have been proposed in the past, and two of them are implemented in the decision tree learner node: the Gini index and the gain ratio. The gain ratio is a measure based on entropy. It is a concept that is used to measure information or disorder. In addition, we can use it to measure how pure a dataset is. To get a better understanding for entropy, let's translate this concept to a dataset with two classes represented as blue dots and red crosses. Mathematically, the entropy is defined as the negative of the sum over the probability for each class multiplied by the logarithm of it. Therefore, the range of the entropy for a binary classification problem is between 0 and 1. To calculate the entropy of the two example datasets, we need the probabilities of the two classes. For the left example, the probability is 7 divided by 13 for red crosses and 6 divided by 13 for blue dots. For the right example, the probability is 1 for red crosses and 0 for blue dots, as we have only red crosses in the dataset. For the left distribution, the formula leads to an entropy of 0.99. For the pure dataset, on the other hand, the formula leads to an entropy of 0. The goal of the decision tree is to isolate all those pure subsets with an entropy of 0. In practice, however, a decision tree rarely finds pure subsets, but in general moves towards pure subsets with a lower entropy. To measure how good a feature is for splitting, we measure the difference between the entropy before and after the split. Therefore, we calculate the entropy before the split and the entropy for each subset after the split. Then we subtract the sum of the entropies weighted by the size of the subsets from the original entropy before the split. This measures the gain in information or the reduction in entropy. We would choose now to split the data on the feature with the highest value in information gain, as this leads to the purest subsets. The algorithm that applies this measure is the ID3 algorithm. This algorithm has the disadvantage of favoring attributes with a larger number of values. The gain ratio measure, used in the C4.5 algorithm, solves this problem by introducing the split info concept. The split info is defined as the sum over the weights multiplied by the logarithm of the weights. The gain ratio measure is then calculated by dividing the gain from the ID3 algorithm by the split info. Another measure for purity, or actually impurity, which is used by the CARD algorithm, is the Gini index. It is based on the Gini impurity, which is defined as 1 minus the sum of the squares of the class probabilities of a dataset. The Gini index is defined as the weighted sum of the Gini impurity for the different subsets after a split. The feature with the lowest Gini index is then used as the next splitting feature. In the decision tree learner node, we can select between the two measures. When it grows the tree, the algorithm calculates the selected measure for all the candidate features to find out which one will produce the best split. But what happens with numerical features? Of course, we don't want to have one branch for each possible numerical value. Therefore, in case of numerical features, the split is always a binary split. In this case, the candidate split points are between every two consecutive values of the numerical features in the training data. Decision trees, like many other machine learning algorithms, are subject to potentially overfitting the training data. Trees that are too deep can lead to models that are too detailed and don't generalize on new data. On the other hand, too shallow trees might lead to too simple models that don't fit the data. You see, the size of the decision tree is of crucial importance. To have a tree that generalizes better, the tree growing phase is often followed by a second phase, the pruning phase. During this phase, the tree is reduced to avoid overfitting. The idea is that we cut branches that have become over-specialized on the training data. For example, branches that are devoted to one single training data sample. Many different pruning techniques are available, and KNIME Analytics Platform provides two: reduced error pruning and minimum description length pruning, MDL for short. In the case of reduced error pruning, the rules of the tree are applied to the training set. If pruning a branch doesn't decrease the accuracy of the training set, the subtree is pruned. MDL pruning, on the other hand, uses the description length to decide whether or not to prune a tree. The description length is defined as the number of bits that are needed to encode a tree, plus the number of bits to encode the samples of the training set that have been misclassified. If the description length for the pruned tree is smaller, we prune the tree. Another option to avoid overfitting is early stopping. To do this, we need to define a stopping criterion in advance. One option here is to define the minimum number of records per node. The branch will stop its growth when a node is created containing less or equal number of samples as the minimum number of records per node. So, a higher value of the minimum number leads to shallower trees, while a smaller number leads to deeper trees. In this video, we have summarized the algorithms used in the decision tree learner node. That is, the C4.5 and the CART algorithm, the information gain and impurity measures, and the pruning techniques available in the node.